Dear students, Assalamu alaikum. In this lecture, we will discuss about the electric potential. Suppose I will draw this figure. Suppose if you have an electric field like this, there is an electric field in this direction like this. Okay, I am having an electric field vector in this particular direction. This is E, right? Understand? For example, now suppose if I have a charge, I have a charge here at this point. Okay, I have a charge Q here. Okay, this charge is at the point A, right? Okay, this is a point A, and I have a charge Q here. Okay, and I want to move this charge from this point to another point B. Okay, I want to move the charge from point A to point B. I want to move the charge Q from point A to point B, right? So you see, you know that due to the presence of the electric field, there will be an electric force on the charge Q, right? So this means that you will have to do some work. Okay, you will have to do some work for moving the charge from point A to point B. Suppose if I want to move the charge through a small distance, okay, suppose if I want to move the charge through a small distance dl, right? Okay, so in that case, the work that you have to do is the small work dw, elemental work dw, will be equal to, okay, it will be equal to minus of F dot dl, okay, where F is the force due to the electric field, and you know that F is given by the force due to the electric field is given by the force on a charge Q due to the electric field E is given by, you can say F is equal to, it's okay, F is equal to Q times E. So if you have the electric field E, the force is given by Q times E. So you can write dW, the small elemental work that you have to do for moving the charge through an elemental length dl, is given by minus Q E dot dl, and this is an elemental length vector. Okay, and the work is not a vector because the dot product of two vectors, right? So now if you want to know what is the work done for moving the charge from A to B, you have to take the integral along the whole length from A to B, right? So you can write the total work, okay, total work for moving Q from A to B is given by W equal to minus Q integral A to B, right? Then E dot dl, right? That is the work that you have to do for moving the charge Q from A to B, right? Now, what is that is for moving a charge of Q coulombs, right? Now, what is the work done for moving a unit charge? Okay, you can represent that as W by Q, right? A to B. Okay, I can represent it as VAB. Okay, VAB equal to W by Q equal to minus of integral A to B E dot dl. Okay, this VAB, you can say that VAB is the potential difference between points A and B. Okay, you can write it as VAB equal to VB minus VA. Okay, so you can say VB is electric potential at A, and this is electric potential at B. Okay, electric potential at A, B, sorry, and this is electric potential at A. Okay, so VAB is VB minus VA. This is a scalar. Okay, this is a scalar. So you can say that potential is scalar. Okay, and there are certain other properties also. We have, so you can say that VAB, see, this is the work done, this is work done for moving unit charge, right? That is 1 coulomb charge. Unit charge from A to B, right? Okay. But you can see, if you have to do some work, okay, if you have to do some work for moving from A to B, then VAB is negative. Okay, you can say VAB is negative, right? VAB is negative if the work is done by the field. That's what it means. Okay, that is, if a charge moves in a field and the movement is due to the work done by the field itself, we can say the VAB is negative. Okay, now if VAB is positive, you can say VAB is positive if an external force does the work. So if you are if a charge is moved by an external force, not by the electric field, okay, in that case actually you can say that VAB is positive. Understand? And the unit of VAB is volts. Understand? That is the unit of VAB, that is volt. Right. Now we will see how to find out the expression for VAB. Okay. You know, you have perhaps in an earlier class we have seen what is the expression for electric field, right? Electric field in general, you can, from the Coulomb's law, From Coulomb's law, you can write it as electric field equal to Q by, right, 4 pi epsilon 0, right, r square AR. Understand? Now, if you have 2 points here, you have a Q here, and because of that Q, you have an electric field, right? You have an electric field due to Q. Okay, you have an electric field because of Q, and you have 2 points A and B. Okay, and I want to move a unit charge from A to B. A unit charge from A to B I want to move, right? So you can write the expression for this as V AV equal to integral minus RA to RB Q by 4 pi epsilon 0, okay, R square, okay, or else we'll do the, instead of writing the magnitude, we can write the magnitude as R square, like this. Then we have AR dot DR AR. Okay, so this will be coming as Q by 4 pi epsilon 0 into 1 by RB minus 1 by RA. That's how you get the expression for the potential difference. Okay, so you can in fact write VA equal to Q by 4 pi epsilon 0 R, and VB equal to Q by 4 pi epsilon 0 RB. Okay, you can write like that. So till now we have defined the potential difference VAB, right? But we can say that at any point, for example, point B, has potential VB, right? Similarly, point A has potential VA. Okay, so these are called potentials or absolute potential. Okay, you can call them potential. Okay, absolute potential, right? And VAB is VB minus VA is potential difference. It is potential difference. Now for the absolute potential, okay, potential difference, we can say that this is the potential at B reference to A. Okay. Potential difference VAB is the potential at B with reference to potential at A. Okay. Similarly, you can say that the potential, absolute potential, you can always say that if you take the absolute potentials VB and VA, they are the potentials at the points B and A with reference to, conventionally it is taken like that, with reference to a point at infinity. Where the potential at that point V infinity equal to 0. Okay. So we define the potential difference like this: VAB is VB minus VA, that is the potential at B with reference to the potential at A. But when we say VB or VA, what we mean is that the potential at B is VB with reference to a point at infinity where the potential is 0. Similarly, the VA is the potential at A with reference to a point at infinity where the potential is 0. Okay. That's how you find out the thing. Understand? Similarly, what you can do is, suppose if you have, okay, many charges. Suppose you have Q1 here, you can have Q2 here, you can have Q3 here. The potential at this point P, you can draw a vector like this, you can draw a vector like this, and draw a vector like this. Okay, this is R1, this is R2, this is R3, right? Okay. So you can write the potential at point P. V is given by, okay, Q1 by 4 pi epsilon 0 R1, right, plus Q2 by 4 pi epsilon 0 R2 plus Q3 by 4 pi epsilon 0 R3. Okay. So you can write the potential due to many point charges. Okay. This is at the point P is given by 1 by 4 pi epsilon 0 into Q1 by R1 plus Q2 by R2 plus Q3 by R3. That's how you can write the potential when you have a lot of charges. Okay. Similarly, if you take a line charge, okay, suppose if you take a potential due to a line charge, you go to a this is a potential due to a line charge. Okay, this is we have to find out the potential due to a line charge, right? You know the electric field due to a line charge is given by rho L, right, by 2 pi epsilon 0 rho 0, right? Suppose if you have a line charge like this, you want to find out the electric field here, you draw a line like this. This is a rho, right? This is a vector rho, right? And the arrow is in this direction, and this is the line charge, right, with the charge density rho L coulombs per meter, isn't it? In that case, you can find out the electric field at this point P as rho L by 2 pi epsilon 0 rho A rho, right? So what will be the potential at point P? Potential at point P due to the line charge is given as VL, okay, integral minus E dot dl, right? So that will be minus of integral rho L by 2 pi epsilon 0 rho, right, A rho, right, dot d rho A rho, okay, because you take a small length and you do the integration dl d rho in this direction, right, and you do the integration. So it will be coming as minus rho L by 2 pi epsilon 0 natural logarithm of rho. Okay, so there will be some constant also. For the time being I am avoiding that constant, right? You can write a constant also plus C. That's okay. Now this is the potential due to a line charge, and I think we'll do a small example so that the things will be clear to you. Example. Okay, you have 2 point charges. Of minus 4 microcoulomb and 5 microcoulomb located at 2 minus 1 3 and 0 4 minus 2 respectively. Okay, so find the potential at 1 0 1 assuming 0 potential at infinity. Okay, so you have V equal to, right, Q1 by 4 pi epsilon 0 R1 plus Q2 by 4 pi epsilon 0 R2, right? That's how you have the thing. You know Q1 equal to minus 4 into 10 raised to minus 6 coulomb, right? Q2 equal to 5 into 10 raised to minus 6 coulomb, right? R1 equal to vector R1 equal to 1 0 1 minus 2 minus 1 3 equal to minus 1 1 and minus 2, right? And you have R2 equal to 1 0 1 minus 0 4 minus 2 equal to 1 minus 4 3, right? So you have magnitude of R1 equal to square root of minus 1 square plus 1 square plus minus 2 square equal to square root of 6. Similarly, magnitude of R2 you can find it as 1 square plus minus 4 square plus 3 square equal to square root of 26. You can find it out, right? Now, since you have found out all those things, you can write the voltage V at the point 101, right? V at the point 101 is 1 by 4 pi epsilon 0. That is 1 by 4 pi into 10 raised to minus 9 by 36 pi, right? 10 raised to minus 9 by 36 pi into minus 4 into 10 raised to minus 6 by root 6 plus 5 by 5 into 10 raised to minus 6 by root 26, right? So you can find it as minus 5.872 kilovolt. That's the answer. Okay, for this question. Okay. Now, suppose if we are in this problem, actually we have taken the zero potential at infinity. One assumption we have made here is zero potential at infinity. Okay, so you can write V equal to Q by 4 pi epsilon 0 R. Okay, for point charge. Okay, you can write like that. And for a line charge, you can write it as VL equal to minus rho L by 2 pi epsilon 0 Ln minus rho L by 2 pi L minus rho L by 2 pi L Ln rho. Okay, you can write like that. Okay, for line charge. Suppose if the zero potential is not at infinity, if reference point or zero potential is not at infinity but at any other point other than infinity, okay, some specified point, okay, then you have to write voltage due to a point charge as Q by 4 pi epsilon 0 R plus C1, and for a line charge you have to write it as minus rho L by 2 pi epsilon 0 Ln rho plus C2. You have to write like that. Okay, if the reference point or zero potential is not at infinity, you cannot choose the infinity as the reference point, but some other finite point, specified finite point, then you have to write the equation like that, and here you have two constants, C1, C2. C1, C2 are constants, okay. Understand? They may be 0 or they may not be 0, okay. So I will try to do a problem to make this point clear. Okay, we have an example too. Okay. You have a point charge. Five nanocoulomb at minus 340, and line y equal to 1, z equal to 1 carries uniform charge, right? Uniform charge 2 nanocoulombs per meter. That's a line charge with a line charge density 2 nanocoulombs per meter. So question A is, if V equal to 0, that is the reference potential 0 is not at infinity but at the origin, you see, at the origin, find V at the point 5, 0, 1. This is what you have to find out. Okay. So in this case, since you can see that the reference potential 0 volt is not at infinity but at a finite point. In this case, it is the origin itself, right? Oh, the point of origin 0, 0, 0, right? So the total potential is due to the point charge as well as the line charge. Okay, so you can see that the total potential V A equal to, right? So you can write V A equal to, what is VQ plus VL, right? And you have some constant, right? So you can write it as Q by 4 pi epsilon 0 R plus C1 plus minus rho L by 2 pi epsilon 0 ln rho plus C2. Okay, you can combine C1 and C2 to make it same thing. So you can write it as Q by 4 pi epsilon 0 R minus rho L ln rho by 2 pi epsilon 0 plus C. Where you can write C equal to C1 plus C2. Okay, you can write like that. That's it. Now we have to find out the different values for this particular case. Okay. Now the potential V equal to 0. Okay, you have VO, right? That is the potential at the point, this thing, right? At the origin. What is it? It is Q by 4 pi epsilon 0, the vector to the origin, right? Okay. Plus minus, right? Minus rho L by 2 pi epsilon 0 ln rho I plus C. Okay. Now you can write VA as Q by 4 pi epsilon 0. You take the position vector of the point A, no, yes, minus rho L by 2 pi epsilon 0, okay, epsilon 0, you can make this as rho 0, okay, ln rho A plus C, isn't it? Now what is VA minus V0, V0 minus VA, okay, V0 minus VA will be equal to Q by 4 pi epsilon 0 R0 minus rho L by 2 pi epsilon 0 ln rho 0, right, minus Q by 4 pi epsilon 0 RA plus rho L by 2 pi epsilon 0 ln rho L, isn't it? Okay. And since V0 is 0, right, we have seen that V0 equal to 0 volt, right? So you can write that V0 minus VA equal to 0 minus VA equal to minus VA. Okay. So you can write minus VA equal to the same thing, isn't it? Q by, okay, the same equation that you have written earlier. Same thing you can write here. That is Q by 4 pi epsilon 0, okay, and into 1 by R0 minus 1 by RA, okay, then minus rho L by 2 pi epsilon 0, isn't it, ln rho 0 by rho I, isn't it? Because you know the identity ln, you have the identity for the logarithm ln rho 0 minus ln rho A equal to ln rho 0 by rho I for the natural logarithm. For the logarithm in general, you can have this identity, right? So I'm using this identity here. So now we will find out what is RA, isn't it? RA and R0 we can find out, isn't it? So first we will find out what is R0. R0 is 0, 0, 0 minus 0, 1, 1, because you are asked to find out the potential at the point 0, 1, 1, right? No. Potential at the point origin from the charge at the point 0, 1, 1. Is it? There's the charge. Sorry, the charge is at minus 340. Sorry, minus 340. The charge is at the point minus 340. Minus 340. Right. So this will be 3 minus 40, and you can find out the magnitude of R0 equal to square root of 3 square plus minus 4 square plus 0 square equal to 5. R0 is 5, right? What about rho 0? How to find out rho 0? We have to find out what is rho 0. It's from the line, right? So you have to find out the potential at 0, 0, right? Okay. The line is given by what? Line is given by y equal to 1, z equal to 1. Those are constant. You cannot change those things, right? And you have to find out the potential at the point 0, 0, 0, right? So x coordinate you make the same as the x coordinate for 0, 0, 0, right? You have 0, 0, 0, right? Then you have dash 1, 1, okay? So x has to be made same, so you make it at 0, right? So rho 0 you can write in fact as rho 0 you can write it as vector rho 0, you can write it as 0, 0, 0 minus 3, 0 0 0 minus, sorry, 0 0 0 minus 0 1 1. Okay, 0 1 1. So we will get it as 0 minus 1 and magnitude of rho 0 equal to square root of 2, isn't it? Similarly, for the case of point A, you can write RA equal to, what is RA? The point A is at 501, right? 501 minus 340, that will be equal to 8 minus 4 and 1, right? So you can write RA magnitude to the square root of 8 square plus minus 4 square plus 1 square, that is 64 plus 16, 81 square root of 81, it will be equal to 9, isn't it? Yeah. And for finding out rho A, you know the line is y equal to 1, z equal to 1, and you have to find out the distance to the point 5 0 1, right? 5 0 1. So you make the same 5 here also. Okay, so you can write this as 5 0 1 minus 5 1 1. Okay, this will be equal to 0 minus 1 0. Okay, so magnitude of rho A will be equal to square root of 0 square plus minus 1 square plus 0 square, that will be equal to 1. Okay, now you can substitute this into the equation. If you substitute into the equation, you can find out the value of, you do the calculation by yourself, then you can find out VA equal to 8.477 volt. That is the answer for VA. Now the second question B, there is another question B, in that you are asked to find out if, okay, I will write it with another pen. If V equal to 100 volt at the point B, at point B 1 2 1. Okay, if V equal to 100 volt at point B 1 2 1. Okay, then have to find V at C minus 2 5 3. Okay, so you can write out, use the same formula as we have used earlier. Okay, you can say that VC minus VB equal to Q by 4 pi epsilon 0, right, 1 by RC minus 1 by RB, right, minus rho L by 2 pi epsilon 0 ln rho C by rho B, right? And if you do the calculation, the same method that we have used now, you will get it as, you know what is VC, isn't it? Now VB, you know, VB is 100 volt, right? VB is 100 volt. So from this equation you will be able to find out VC equal to 49.825 volt. So what you have to do is you have to find out RC, RB, rho C, rho B, etc. using the same method that we have used in question. Okay. So this is the third part of this question. The third part of the question is given by question C. Okay. If V equal to minus 5 volt at 0, the point O, find VBC. Okay. So you are given V0 equal to minus 5. Okay. V0 is equal to minus 5. So you have to find out VBC. Okay. In this case, what we have to know is you have to find out VBC. Okay. So what you have to do is same formula you can use, that is Q by 4 pi epsilon 0 into 1 by RC minus 1 by 1 by RB. Okay. Then minus rho L by 2 pi epsilon 0 ln rho C by rho B. Find out RC, RB, rho C, rho B, and all other values are given. So you can find out the answer as minus 50.175 volt. That's the answer you will get for that particular problem, right? So that's about this potential, and I will stop it here. Thank you.